Has another one of OpenAI's new models just solved another famous maths conjecture? The conjecture is called the Cycle Double Cover Conjecture, and it's something I'm going to explain shortly. 3 days ago, on July 10th, an OpenAI employee called Ethan Knight tweeted that the new public model GPT 5.6 Sol Ultra solved the Cycle Double Cover Conjecture in under an hour with 64 subagents being used. And this already comes off the back of another famous piece of news that came out recently, where one of OpenAI's models solved the unit plane conjecture, which is a famous Erdos problem. It's widely believed that the AI's proof is correct now. Mathematicians such as Tim Gowers said so and commented on the proof and its kind of elegance, and it's all about trying to position as many points in the plane as possible that are all a unit distance away from each other. And the AI actually disproved this conjecture in the sense that it developed a counterexample. So it went against the grain of thought, which is also very interesting. So the main object of interest for this theorem that I'm about to get onto is undirected graphs. This is like a set of vertices or points connected by edges, and there can actually be several edges between two pairs of points, so parallel edges. And furthermore, we're interested in something called cycle double covers. So a cycle is just a subgraph within the graph of interest, such that you can basically start at a point and then travel to a bunch of different vertices and then end up at the same point. It's a cycle just as you think it would be. And particularly, a cycle double cover is a collection of cycles on this graph, such that each edge is represented twice in this collection of cycles, right? So that's where cycle double cover comes from. Each edge is being covered doubly. So as a basic example, we can think of the graph K4. I'm going to get it up on the screen. It's like a square with an X. All the vertices are fully connected with the other vertices. And if you think of the 4 right angle triangles that you can make from that image, they're all cycles. And in fact, they cover each edge exactly twice. And so that collection is a cycle double cover. Wikipedia also has a nice picture of the Peterson graph. That's like a pentagram with vertices coming off each kind of vertex of the pentagram, and that has a cycle double cover as well. The final object of interest is something called a bridge in a graph, which is just an edge whose deletion would increase the number of connected components within the graph. That sounds very technical, but basically if you have like a kind of square here and a square there, graphs, and then there's one edge connecting them, that's one entity. But if you then deleted that edge, you would have 2 separate entities or connected components. And therefore, that edge that we deleted is called a bridge because it acts as a bridge between these connected subcomponents. And so finally, the theorem that OpenAI seemingly proved is the cycle double cover theorem, which says that every bridgeless graph, with a few extra details, has a cycle double cover. And we've just looked at 2 examples of the K4 graph and the Peterson graph, which both have cycle double covers. I want to quickly comment on the prompt that was used before we go on to the proof, because it's pretty interesting in the way that they've tried to explain the task to the model. The prompt starts off fairly benign, explaining the problem that we wish to solve and all the main objects of interest. And then it says something weird like, assume that there does exist a proof to the following problem. And I already think that's quite an interesting thing to tell an AI. It's basically motivating the AI to not give up early and to assume a proof exists. We actually do this to students all the time in exams, right? When a student is posed with a question in an exam and they spend a bunch of time doing it, they can be rest assured that there does actually exist a solution to the problem. Like, they're not just going to sit and waste their time for a few hours, unless it's a really unfair exam maker. So the same kind of approach is being done to an AI here to make sure that it doesn't chuck the towel in because the task seems hard. The prompt also explains how to use its agents correctly to ensure that it has a diverse portfolio of different strategies. It says to keep trying a bunch of different strategies and not kind of give up too early on any one of them, but also to not just go down one rabbit hole, especially if it doesn't actually ease the difficulty of the problem at all, and it basically turns into solving an equivalently and equally as difficult tough problem. And basically it tells the model not to home in on any one of these approaches too early. And this is really interesting because mathematicians home in on approaches all the time, and they give up on approaches which don't seem very ripe or fruitful or boring, and they go down it for a bit and then they kind of give up. Whereas we can just make a AI model try 60 different approaches for as long as we can afford to run the model, which is pretty cool. And I guess we don't care how long an AI model is going to be working for, you know, until they start to unionize. It also says do not return if results are not found or it seems very difficult, and only return a proof when it survives a serious adversarial audit. Finally, spend up to 8 hours on the problem, and do not go online to check whether the CDC is an open problem, and do not come back to us and tell us that the CDC is a difficult open problem. Basically, forget it's a famously difficult problem and just do it. Sit down and do the work is basically what the prompt is saying. So yeah, I think it's a pretty funny prompt, and I recommend that everyone should read it. It's like 2 pages, and honestly, it's pretty interesting seeing how you can direct a model to do hard things. I'll briefly comment on some of the steps of the proof, although I'm by no means an expert. So basically, they say that it suffices to show that you can always find a cycle double cover for cubic graphs. Cubic graphs are where each vertex has a degree 3. This is because if you have vertices of degree 2, then you can kind of like get rid of them, and you can transform the graph in such a way. This is basically because for vertices of degree 2, you can just cut them away and end up with vertices of degree 3 or higher. And for vertices of degree 4 or higher, you can basically transform those vertices into like a bunch of smaller vertices with a degree of 3. And you have this transformed graph, which you can find a cycle double cover for, and that implies that there will be a cycle double cover for the original graph. So you can just worry about cubic graphs, which greatly reduces the problem's complexity. The proof also uses something called an 8-flow theorem, which is basically it assigns a numerical value, like a amount of flow coming in and out of these edges, even though they're undirected, and it basically says that the flow in equals the flow out at any vertex, and it turns out that an 8-flow does exist for any of these cubic graphs. The proof then shows that you can do a certain kind of assignment to every edge of the graph, and that such an assignment kind of produces a cycle double cover, and it's about just 2 pages of showing that such an assignment is possible and showing that such an assignment leads to a cycle double cover. And so all cubic graphs have cycle double covers, and that implies that any non-cubic graph also has a cycle double cover, because they can be reduced to a cubic graph that has get a cycle double cover for that, and then that implies that there's one for the original. So is the proof correct? Well, I'm not sure. I'm not a graph theorist. It certainly passes a sniff test, and there's a mathematician called Thomas Bloom who has gone on record and said that the theorem, the proof rather, is very nice and elegant. But there has been reported false proofs of this conjecture before, so we need to be very careful before we start like waving our flags and saying, oh my god, AI has solved another proof. What really needs to happen is more mathematicians need to read over this and give a greater consensus that they think this is correct, and moreover, I think it needs to be formally verified in a theorem prover such as Lean or Isabelle, which is basically a system which you can encode the kind of argument and proof into, and then it can mechanically check each step and make sure that no logical details were swept under the carpet. So if someone could formalize this and get it formally verified, that would give great credence towards it being a correct proof. The only problem is it's reported that Lean's graph library, and I know myself that Isabelle's graph library, are not strong enough and don't have enough like exotic formalizations of precursor definitions and stuff in order to prove these things. So we're still, in the short term, quite far from being able to formally verify that this thing is correct. But I do think it's a worthwhile endeavour rather, as knowing whether this proof is correct or not is a really big deal, because it is a genuinely historical thing if an AI model has again proved quite a significant theorem that has stumped very top mathematicians for 50 years. And it's done it in an elegant way. It makes you wonder, are there more elegant proofs out there? So yeah, this is an interesting story about the future of maths, the way AI intersects with it, and what sort of tools are we going to need to use in order to ensure that we've not got rose-tinted glasses on and that we're actually checking that the outputs of these models are correct. And I think formalization and theorem proving is certainly one of these things.